We're always looking for those, those big leaps forward, aren't we?
Absolutely. The breakthroughs.
Whether it's a scientific discovery or maybe a game-changing algorithm.
Yeah, but that traditional path, it can take so long.
Oh, definitely. The brainstorming, the exploring the unknown, endless experiments, proving it all. It can feel like a real slog sometimes.
It really can. It's a huge investment of time, resources, dedication, of course, but still massive.
Exactly. And I think that's why there's been so much excitement, buzz around large language models, LLMs.
The potential is huge.
Yeah, the idea that we could maybe automate parts of that process, especially with these new agents that can understand language and act.
It's definitely exciting. We've seen them do well on benchmarks, even suggest hypotheses or experiments.
Right. But going from that, from automating tasks we already know how to do to making genuinely new discoveries,
Yeah,
that's been the real challenge, hasn't it?
it has. That's a significant jump. Yeah.
But get this. Today, we're diving deep into something new, aiming to bridge exactly that gap. It's called AlphaEvolve.
Right.
It's a coding agent powered by LLMs, but its specific goal is making new scientific and practical breakthroughs by, by evolving algorithms.
That's a good way to put it, like AI breeding better ways to solve problems.
Exactly. Okay, so let's unpack this. Our mission today, using the great sources you shared, is to figure out how AlphaEvolve actually pulls this off. What makes it different, and we'll look at some of the pretty surprising breakthroughs it's already made.
Yeah, in mathematics, computer science,
Yeah.
even inside Google's own systems.
Okay, so where do we start? What's the core idea?
Well, what's really interesting is the basic principle. The user defines the what. So the problem you want to solve and how you'll measure success, the evaluation criteria.
Okay, so I tell it the goal.
Exactly. And then AlphaEvolve figures out the how. It iteratively evolves and refines algorithms to meet that goal.
So instead of a person carefully crafting the solution step by step, AlphaEvolve is kind of like this tireless optimizer, just constantly tweaking the code.
Precisely. Like a recipe generator that just keeps getting better and better.
And you mentioned something interesting. The goal isn't always the final algorithm itself.
Right. Sometimes the goal is actually to find an algorithm that can then find the solution you want.
Ah, okay. So it might create a search method rather than the answer directly.
Exactly. And that indirect approach can sometimes be much more powerful, unlock things you wouldn't find otherwise.
Okay, this is where it gets really interesting, right? The how, it uses an evolutionary strategy, like natural selection.
Very much like that, yeah. It starts with some initial program, maybe something pretty basic.
Okay.
And then it goes through these cycles, generating new versions, modified versions, testing them out.
And the engine driving that evolution, that's the LLMs.
That's the key. The LLMs are crucial for responding to the feedback from those tests.
So they see what worked, what didn't.
Exactly. And they could suggest improvements, find new directions, maybe things that are quite different from where it started. It's not just small tweaks.
Wow. It sounds like a really sophisticated feedback loop. Can you kind of walk us through the stages?
Sure. At its heart, it's this evolutionary loop. It starts with something called a prompt sampler.
Okay, what's
It's basically a smart way to create the questions, the prompts for the LLMs. It looks at past attempts, good ideas, maybe even bad ones.
so it uses history to frame the next question.
Right. Those prompts go to the LLMs, which then propose improved programs or maybe just modifications.
Got it.
Then evaluators kick in. These automatically score the new programs based on the criteria the user set up.
What we talked about earlier.
Exactly. And finally, all the programs, their scores, goes into a program database.
Which acts as memory
Yeah.
and inspiration.
Both, yeah. It tracks what's been tried and provides material for the prompt sampler in the next round. It just keeps iterating.
It sounds like this continuous cycle. Learn, improve, repeat. Now, this isn't the very first attempt at this, right? You mentioned Fun Search before. How is AlphaEvolve different? What's the step up?
That's a really important point. AlphaEvolve is a significant leap forward in quite a few ways. First off, it evolves entire code files. Fun Search just worked on single functions.
Okay, so it can handle much more complex algorithms.
Way more complex. We're talking hundreds of lines of code compared to maybe 10 or 20 for Fun Search.
Wow, that's a huge difference in scale.
It is. Second, Fun Search was pretty much Python only. AlphaEvolve can work with basically any programming language.
Much broader applicability then.
Definitely. Another big difference is evaluation time. Fun Search needed really fast evaluations, like under 20 minutes.
Right.
AlphaEvolve can handle evaluations that run for hours, even using specialized hardware in parallel.
So it can tackle much tougher, more computationally heavy problems.
Exactly. And interestingly, it does this using far fewer LLM samples. Thousands, maybe, compared to millions for fun search.
Fewer samples, but better results. How?
Well, it seems to benefit much more from the newer, state-of-the-art LLMs. Fun search didn't get much boost from bigger models.
Ah, so the quality of the LLM matters more now.
It seems so. And the prompts themselves are much richer. More context, more feedback, not like the minimal prompts Fun search used.
Okay.
And one last thing. AlphaEvolve can optimize for multiple goals, multiple metrics at the same time. Fun search just focused on one.
Right, so it's handling more complexity, broader languages, tougher problems, using better LLMs more effectively, and optimizing more things at once. Quite the upgrade.
It really builds on those foundations, yeah.
Okay, going back to the user defining the what. You said they provide evaluation criteria. How does that work in practice? What do they actually give the system?
So the user needs to provide an automated way to judge the solutions, basically a function.
A piece of code?
Yeah, a function that takes a potential solution from AlphaEvolve and spits out some numbers, some scores. AlphaEvolve's job is then to find solutions that make those scores as high as possible.
Can you give an example, like for a specific problem?
Sure. Let's say you're looking for the largest possible graph that has some special property. The evaluation function could just return the number of nodes in the graph AlphaEvolve generated. Bigger graph, better score.
Simple enough. What about more complex cases?
Well, maybe the thing AlphaEvolve evolves is a search algorithm. The evaluation function might then run that search algorithm on a test case and score how well it performed. Or it could even involve training a machine learning model that AlphaEvolve created and scoring its accuracy. The key thing is it have to be automatic.
Right. Needs that clear, objective ruler for the system to measure itself against. Makes sense. Now, you also mentioned its flexibility and abstraction. What does that mean exactly?
Yeah, that's about how AlphaEvolve tackles the problem. It's not just stuck evolving the final answer directly.
Okay.
It can evolve raw code strings, sure, but it could also evolve things called constructor functions, like blueprints for building a solution. Or, as we mentioned, it could evolve entire search algorithms designed to find the best solution within a time limit.
So different levels it can operate at?
Exactly. And
Yeah.
sometimes it even co-evolves things like it evolves intermediate solutions and the search algorithms that improve them, making the search specifically good at refining those kinds of solutions.
Wow. So how does it choose? How does it know which level of abstraction is best?
Well, our thinking is it depends a lot on the problem itself. Its characteristics.
Like what?
Like, if the solutions you expect are highly symmetric, maybe evolving those constructor functions, those blueprints, is more efficient because they can capture symmetry concisely.
Right.
But if the solutions are more complex, less predictable, maybe evolving a custom search algorithm is the better bet. It's like having different tools, and it learns which tool to use for which job.
That's pretty smart, adapting its whole strategy based on the problem. And you mentioned state-of-the-art LLMs are key. Which ones is it using?
It's using a combination, actually. Gemini 2.0 Flash and Gemini 2.0 Pro.
An ensemble? Why both?
It's about balancing speed and quality. Gemini Flash is faster, lower latency.
So more exploration.
Exactly.
Yeah.
It lets AlphaEvolve generate and test more ideas quickly, cover more ground. But Gemini Pro, while maybe a bit slower, has more overall capability.
For the deeper insights.
Right. It can sometimes come up with those higher quality, more innovative suggestions that really push the search forward or lead to a big breakthrough. It's like having a rapid brainstormer and a deep thinker working together.
Speed and depth. Makes sense. Okay, let's talk about those prompts again. You said they have long contexts. What actually goes into a prompt to guide the LLM?
They pack in quite a bit, obviously some promising solutions found earlier.
Okay.
Specific instructions on how to suggest changes, but users can add a lot more context too.
Like what kind of context?
Fixed instructions, maybe relevant math equations, code snippets that could be useful, even whole research papers as PDFs.
You can read PDFs.
Yeah, it can ingest that background information, draw on existing knowledge.
That's powerful, not just looking at the code in isolation.
Exactly. And to keep things diverse, the prompts can use stochastic formatting, like having multiple ways to phrase something and picking one randomly.
Introducing some randomness.
Controlled randomness, yeah. And crucially, the prompts show the results from previous step, runs the code, its output, the scores it got.
So the LLM sees the consequences of past suggestions.
Right. And there's even this idea of meta-prompt evolution, where the LLM itself helps refine the instructions for future prompts.
Whoa. Okay. The AI is learning how to ask itself better questions over time. That's really meta.
It is.
So when the LLM suggests a change, how does that get applied, especially in big code files?
For larger projects, it usually uses a specific diff block format.
Like programmers use for version control.
Sort of, yeah. It's like
Yeah.
search, then the old code, the new code, and replace.
Very specific. Find this, replace with that.
Exactly. It's crucial for making targeted changes without messing up the rest of the code, like a surgical edit.
Makes sense for big projects.
But if the code is really short, or if a complete rewrite seems better, it can also just output the whole new block of code directly. It's flexible.
Got it. Okay, let's circle back to that evolutionary database you mentioned. Storing all these solutions. How does it manage that? It must generate tons of them.
Yeah, the main job of the database is to organize all that and bring back good ideas later. It has to balance exploring new, different ideas with exploiting the best ones found so far.
The classic exploration versus exploitation trade-off.
Exactly. It uses an algorithm inspired by a couple of ideas: MAP elites and island-based models.
Okay, what do those do?
MAP elites tries to categorize solutions not just by how good they are overall, but also by their characteristics, their features. Keeps diversity.
So not just the best score, but different kinds of good solutions.
Right. And island models kind of simulate separate populations evolving independently, but occasionally sharing good ideas.
Ah, like different research groups sometimes converging.
Sort of, yeah. It helps maintain diversity and prevents getting stuck too early on one path. It's about organizing the ideas effectively.
Smart. And all this computation the LLM calls, the evaluations must be huge. How is it structured?
It's built as a distributed pipeline, asynchronous.
Meaning things happen in parallel.
Yes, some things run at the same time using Python's Asyncio. You have controllers managing things, LLM samplers talking to the models, evaluation nodes running the code.
Like an assembly line.
A very concurrent assembly line, yeah. The goal is throughput, maximizing how many ideas get explored and tested within the budget, not necessarily how fast any single step is.
Right, getting the most evolution done. Okay, I think I've got a decent grip on the how. Let's get to the results, the breakthroughs. Matrix multiplication first. That sounds fundamental.
Oh, it is. Absolutely core to so much computing. Machine learning, graphics, scientific simulation, you name it.
And finding faster ways to do it is hard.
Extremely hard. We've known since the late 60s, thanks to Strassen, that the standard way isn't the fastest. Better methods involve decomposing this 3D tensor object.
Okay.
And the rank of that decomposition tells you how many multiplications you need. Lower rank means a faster algorithm.
But finding lower ranks is the tricky part.
Very tricky. Even for small matrices like 3 by 3, we still don't know the absolute minimum number of multiplications needed. It's been an open problem for decades.
Wow. So what did AlphaEvolve achieve here?
It made real progress. It improved on the known best algorithms for 14 different matrix multiplication sizes or types.
14. Any standouts?
Yes, the big one was for multiplying two 4x4 matrices.
Yeah.
The best-known algorithm needed 49 multiplications. That record stood for 56 years.
56 years. And AlphaEvolve.
Found an algorithm using only 48 multiplications, specifically for complex numbers. But still, it broke that long-standing barrier, a major open problem.
That is incredible, shaving off one multiplication after half a century.
And sometimes these complex number algorithms can be used for real numbers too, for certain sizes. The changes it made weren't trivial either. It tweaked the optimizer, initialization, loss function, hyperparameters, significant stuff.
So this isn't just theoretical, that one multiplication less could actually matter.
Oh yeah, it cascades. Faster matrix multiplication means faster AI training, faster simulations, real-world speedups.
Amazing. Okay, what about the second area? Tailored search algorithms for open mathematical problems.
Right. This is about finding mathematical objects with optimal properties. Think like the densest way to pack spheres.
The kissing number problem you mentioned.
That's one example, yeah. Or finding functions with very specific complex properties. AlphaEvolve was turned loose on over 50 of these kinds of problems across different math fields.
50. How did it do?
The results were pretty stunning. In about 75% of cases, it rediscovered the best-known solutions on its own.
Okay, so it could match human mathematicians often.
But in roughly 20% of cases, it actually beat the state-of-the-art, found new, better constructions.
Like what?
Well, it improved the bound for Airdrie's minimum overlap problem, how much geometric shapes have to overlap.
Okay.
And it improved the lower bound for that kissing number problem in 11 dimensions, from 592 to 593.
Finding room for one extra sphere in 11 dimensions. That sounds incredibly difficult.
It is. These are subtle but significant improvements. It also found new results for packing hexagons inside hexagons, minimizing distance ratios between points, variants of the Heilbronn problem about smallest triangles, packing circles in squares and rectangles. Lots of stuff.
So how did it do that? By evolving the search algorithms themselves?
Exactly. Instead of directly evolving the packing or the function, it evolved heuristic search algorithms designed to find good packings or functions.
Ah.
Give the search algorithm a time limit, maybe the previous best solution to start, and let it refine things. It often discovered these complex, multi-stage adaptive strategies that are really hard for people to come up with.
So it learned how to search better for these specific problems.
Precisely.
Yeah.
And many of these problems were suggested by mathematicians, showing a nice potential synergy there.
AI discovery guided by human intuition. Very cool. Okay, third area, optimizing Google's own computing ecosystem. This sounds very practical.
Hugely practical.
Huh.
Because Google operates at such immense scale, even tiny percentage improvements can mean massive savings in resources or energy.
Right. So what did it do?
First, data center scheduling. Inside Borg, Google's cluster manager, they have this issue called resource stranding, like a machine has CPU free, but no memory, so you can't schedule a job.
Wasted resources.
Exactly.
Huh.
AlphaEvolve looked at this as the bin packing problem, fitting jobs, items, into machines, bins, with multiple constraints, CPU memory. It discovered a surprisingly simple but very effective new heuristic function for deciding where to place jobs. Simpler and better than the one they were using in production.
How much better?
It resulted in recovering about 0.7% of compute resources on average, fleet-wide, which sounds small, but at Google scale, that's huge.
Wow. And they preferred it over, say, deep reinforcement learning.
Yeah, because the heuristic AlphaEvolve found was interpretable, easier to understand and debug, critical for these core systems.
Makes sense. What else within Google?
Optimizing compute kernels for training models like Gemini, specifically Palace kernels on TPUs. Getting the tiling strategy right, how you break down big matrix multiplies, is key for speed, but super complex manually.
Okay.
AlphaEvolve optimized the tiling heuristics, minimizing runtime while guaranteeing correctness, because it only changed the tiling part.
Nice.
It also optimized low-level arithmetic circuits in the TPUs themselves, found a simple code change in the hardware description language, Verilog, that reduced circuit area and power, got validated by the TPU designers.
Directly improving the hardware design.
And finally, directly optimizing compiler output. It took the intermediate code generated by the XLA compiler for the flash attention kernel important transformers and found ways to speed it up.
How much?
A 32% speed up in the kernel itself and 15% in the surrounding processing. Shows potential for building this kind of AI optimization right into compilers.
These are seriously impressive practical results across the board. Now, to be sure these results weren't just luck or that one part was doing all the work, you did ablation studies, taking parts away to see what happens.
Exactly. We did that for the matrix multiplication and kissing number problems. We looked at disabling the evolutionary part, removing the rich context from prompts, turning off meta-prompting, going back to single-function evolution using less powerful LLMs.
And what did you find?
Basically, everything mattered. Each component, the evolution, the context, the meta-prompts, the full-file evolution, the powerful LLMs, each contributed significantly. Take one away, and performance dropped noticeably.
So it really is the combination, the whole system working together.
It seems to be, yes. The synergy is important.
Okay, looking ahead then, what are the main limitations right now?
The biggest one is definitely the need for that automated evaluator.
The automatic scoring function.
Right. That works well for math, computer science, where you can often programmatically check or score a solution. But it limits applying it directly to domains where evaluation is harder, more subjective, or needs physical experiments.
So designing a new drug molecule where you need lab tests or writing a novel where quality is subjective, those are harder for this current setup.
Exactly. Now, it can incorporate feedback from LLMs themselves on ideas. We just haven't focused on optimizing that yet. There's other work exploring using LLMs for that kind of high-level feedback where automated scoring is tough. Combining those could be a future direction.
Makes sense.
And, another interesting thought is, could AlphaEvolve eventually improve itself? Improve the LLMs it uses, or its own infrastructure? The feedback loops are long right now, but it's an intriguing possibility down the line.
Self-improving AI, always a fascinating prospect. So, wrapping up, AlphaEvolve feels like a really potent combination, doesn't it? State-of-the-art LLMs, automated evaluation, evolutionary methods.
Yeah, it's demonstrating a powerful synergy, tackling problems that have been open for decades and also delivering real practical improvements to complex systems.
And the solutions it finds. Often surprising, not what a human might immediately think of.
Definitely. It points towards a new way of doing science and engineering, driven more by AI discovery.
It really does make you think, doesn't it? Consider the implications. AI that doesn't just solve problems we pose, but designs the very methods to find new knowledge, optimizes the systems we rely on. What kinds of breakthroughs could be next with tools like AlphaEvolve constantly learning and evolving? That's certainly something to ponder after this deep dive.